In this video today, I'm going to show you how to solve all projectile problems. I don't believe that there are different kind of projectile problems. I think they're all the same. They all have the same basic parts, and if you approach them all the same way, they really are very straightforward to solve. And we've already learned about some of the concepts, so I'm not going to review that now. But we know that every projectile has to start off with some kind of initial velocity. Now that could be something like this, something like this, something like this. These are all possible initial velocities, and that usually the problem tells you that, but sometimes that's the point of the question. Every projectile is going to start off with some initial angle, and typically that angle is going to fall somewhere between 90 degrees, 0 degrees, or negative 90 degrees. So if you come back up here, this arrow would be something between 0 and 90. This would meant to be 0, and this would be something this would be a negative angle. All right, so every projectile has an initial velocity and an initial angle. Now we've learned already that in a projectile motion there is horizontal motion and vertical motion, and the two are independent of each other. One does not affect the other at all. We know that gravity is the only force acting on a projectile, so the free body diagram of a projectile is quite simple. It looks like this. That's it. Weight down. And we know that weight is mg, so that means for every projectile, mg equals ma on the y-axis, and the mass divides away. So the acceleration on the y-axis is identical in value to g, which on the planet Earth is 9.8, and since down is negative, we'll say the acceleration due to gravity is negative 9.8. Well, to start a projectile problem, first thing I always do is start up here, and you should be very organized. Write down your initial velocity and write down your angle. Horizontally, we know that A is 0. There's no force on the horizontal axis because we're assuming no wind resistance. And so because there's no acceleration, the only important values horizontally are the initial horizontal velocity, the time, and what is your initial position and what is your final position. And of course sometimes these two are lumped together to be delta x. Vertically, well, everything's in play. Vertically, the acceleration is negative 9.8. Then there's the initial velocity on the y-axis. Over here I should have put x. And then there could be a final velocity on the y-axis, time, and an initial position vertically, and a final position vertically. So for every single projectile problem, you write down this information, and then you read the problem, and you establish what you know and ultimately what you're looking for. Before I finish though, let's review this. Let's go back to the initial velocity and up here. I should have mentioned this sooner. We always think about if an object has an initial velocity at some angle theta, then we know that it contains that initial x velocity as well as an initial y velocity. Now of course we recognize this right triangle. This is something we've been working with a lot, and so we know that Vix has to be equal to Vi times the cosine of theta, and Viy will always be Vi times the sine of theta. So now you have all the information we need to solve any projectile problem. So now what I'll do is I'll go through several examples and show you that you just set this template up and then fill in the numbers in, and we will solve the problem from there. the little boy tries to impress his mother by running off the diving board. His velocity is 5 meters per second, and the diving board is 3 meters above the water. How long does it take for the boy to hit the water? Well, this is a classic example of a projectile problem. It's often referred to as a horizontal projectile problem because the boy is strictly running horizontally when he becomes a projectile. So, you notice I've already started by having some of my basic stuff over here. Just from reading the problem, I realize that his initial velocity is 5, and his initial angle is 0 degrees. Since when he leaves the diving board, that's his direction. Therefore, VI x will be equal to 5 times the cosine of 0. Well, that works out to be 5, and VIY is 5 sine of 0, which actually ends up being 0. So in a horizontal projectile, all your initial velocity is horizontal and none of it is vertical. If you do enough of these, you'll probably end up skipping this step and just jumping right to, in this case, 5 and 0. There's a change in x, and there's a time. Over here, acceleration is negative 9.8. Let's make it negative 10. Make it easier. His initial y position would be 3 meters, and his final y position would be 0. If we make the water the lowest point being having a height of 0. There's, of course, his time, and there would be a final y velocity. So I think I've written down all the important information. Now, the question is, how long does it take for the boy to hit the water? Which means that is the answer right there, the time. Well, this is just a kinematics problem. You already know the formulas to do this. In this case, you notice I have an initial velocity, I have an acceleration, I have position, I'm looking for time. The one thing I don't have anything about is the final velocity. That's okay. I got a formula that handles that. YF equals 1/2 AT squared plus VI, in this case YT, plus YI. So fill in some numbers here. 0 equals 1/2 times negative t squared plus 0 plus 3. So now I have 0 equals negative 5 t squared plus 3. Negative 3 equals negative 5 t squared. So t squared is equal to 0.6, making t equal to 0.77 seconds. So the boy takes 0.77 seconds to hit the water from a diving board that is 3 meters high. Now you'll notice we didn't do anything over here. That's okay. We didn't need to, based on the particular question that was asked.